Okay, are we ready? Shall we start? Do you remember that last lecture? Now we get to do it all over again. This time I will use the NACA 0012 tutorial and I will go through it step by step. Here you have one file, NACA 0012.case. This is a Fluent mesh file and not an OpenFOAM file. So just to show you the difference, I will show you what that one looks like. See? Completely different format. Okay, so in my case directory, I have 0, constant, system, and I have this little thing called save that I will speak about later. Can you read that text without any trouble? Is that better? So in my system directory, I have control dict. We said everything that starts with /* and ends with */ is a comment. Okay? Everything that starts with // is a comment line. The rest of the line is ignored. Okay? All of the input-output files are in dictionary format, and the dictionary goes through the parser. Okay? I will show you later what that means. For the moment, you can ignore the comments. You remember this part here? We said this is a dictionary. The name of the dictionary is foam file. Starts with an open curly bracket, ends with a closed curly bracket. It says version 2.0. This is not the version of foam that you're running. This is the version of the input-output system. We changed it once in 20 years, so it's not too bad. Okay? I don't think we will end up at 3.0 anytime soon. The second thing is it says format ASCII. Okay? If it says format binary, it does not mean that the whole of the file is in binary format, and I will show you a little bit later what it means. Okay? It means that only the heavy-duty data of fields like pressure, velocity, temperature, velocity gradient, etc. is in input-output. The rest is still in dictionary format. Then it says class dictionary. Okay, so it tells you object of which class lives in this file, and the object name is control dict, which should be the same as the name of the file that I'm looking at. Okay, later on we will talk about consistency, but all things in good time. Okay. For start, it will say application, simple foam, and that is the name of the tutorial solver that we will be running. And then it says start from, start time, stop at, end time, delta t, write control, write interval. Do you recognize this? Okay, so start from, start time is 0, stop at, end time is 1000, delta t is 1. Since simple foam is a steady state solver, the size of the time step doesn't matter. If you specify it to be 0.033, it will count 0.033, 0.66, 0.99, etc., which is a bit more difficult for my son than 1, 2, 3, 4, 5. So usually we use delta t equals 1. What happens if your solution depends on the time step size in the steady state solver? Well, something is terribly wrong. Okay, so in this case, this should not happen. Further to that, we have the second part of things that I have already described, and now I'm going to show some more of them. Purge write. Okay, what does that mean? If you're running on an HPC cluster and they give you 100 megabytes of data, you cannot afford to save 500 time dumps. Okay? So what we do is we set purge write to 3, and then it will write 0, 50, 100. When it writes 150, it will delete 50. When it writes 200, it will delete 100, etc. Okay? Keep in mind that nasty people running HPC clusters, we should be pointing fingers now, right? Can kill your run while it's writing. Okay? So you at least have to have 2 of these directories for you to restart. Otherwise, there is trouble and lots of CPU time wasted. Okay? Write compression. You can say compressed or uncompressed or even on or off, which basically tells you whether you write a file u or u.gz. gz stands for gzip, and foam will happily read and write gzip files, and I heartily recommend that you write everything in the compressed format. Why? Number 1, you save disk space. Number 2, actual reading and writing is faster. You're reading a smaller file, and then you're using the CPU to unzip it on the fly to the full size. Time format. You can have general, or you can have scientific if you write 1.0 E plus 00 for 1. And there's probably some other choices. Runtime modifiable, we spoke about. And then there is this nice entry down here called functions. See what I've got here? Nothing. Okay, they all start with // Yes, sir?
The write compression compressed, that's not the default value, is it?
Well, we changed the default about 2 months ago. Okay, so it is a default for me, but not a default for you. Okay, and would you like to have it as default?
I think for our usage it should be default, because we've noticed that the storage is being stressed a lot and it's not being used compressed.
I have a great idea.
Okay.
You have the source access. Why don't you change the default? Okay? We can take a look and do it. Or you can just override it and write everything in a compressed file format if you wish. Okay.
There's no negative impact from using compressed?
Well, you save less files, the files are smaller, and reading and writing is faster. Okay, and if the file is corrupted, it's corrupted, so you're dead anyway.
Does it compress every file separately, or does it make...
It compresses every file separately.
Okay.
Okay, I will show you that in about 5 minutes. Okay, now, do you remember what we spoke about on the fly post-processing? Okay, so in the control dictionary, we have a way of adding something called a function object, which means there is a little piece of code that executes once per time step. And when we uncomment this one, it will calculate the forces on the patch wall with some other parameters, but because things can go wrong, currently all of this is commented out. Okay, so the next thing that I would like to do is I would like to take a look at the mesh. And there is no mesh. Remember, I promised you a polymesh directory, and there isn't one here. So the first step of my tutorial is I will show you my favorite way of generating meshes, which is stealing them from other people. Okay? So here we have a naka0012.case, which is a Fluent case file containing the mesh. Okay? I also told you that the mesh has got a specific format in OpenFOAM. So if I ask you to write one by hand, you're going to kill me, right? Okay, so in that case, let us convert the mesh from Fluent format into OpenFOAM format. And for that, we will use a tool called, guessing, exactly, Fluent Mesh to Foam. Okay. Fluent Mesh to Foam. And if I click enter, what will happen? Well, not good, right? Because it will say Fluent, usage, Fluent mesh to foam, Fluent mesh file, and then a whole bunch of options. Okay, so obviously I had to tell it which Fluent file to get. Okay, and the most important part of the message is this thing here. Foam, fatal error, wrong number of arguments, expected 1, found 0. Or, dear Herb, you forgot to give me an argument. Okay? Shall we do it properly now so that we don't have 2 errors one in a row? Okay, I said Fluent mesh to foam, Naka 0012. At the top, I am going to have some polite things happening. Okay, so number 1, it will write out the banner saying this is Foam Extend version 3.2, blah blah blah. There is the git build ID. The executable line said Fluent mesh to foam, Naka 0012. The date is 3rd of May 2016. The time at home is 10:03:48. The host is Temple. The process ID is this. The control dictionary is that. The case is Naka 0012. Number of processors is 1. All clear? So if your run is running for 2.5 weeks and you want to know which process ID to kill, it will be that one there. Okay? It will also tell you what machine, etc. And from that point onward, it will actually start doing its job. Okay? So down here, it will say, create time. What that does is it reads system control dictionary, and then it will analyze the Fluent mesh file. It will say number of cells, 760, 80, reading kinds of faces, blah, blah, blah. And in the end, it will say something like writing mesh to constant polymesh done and end. So now, inside of constant polymesh, I have a bunch of files. Okay, so let's take a look at the first one of them. Does it look familiar? Okay, banner, I don't care. Foam file, version 2.0, format ASCII, class, vector field. What did it say the last time we looked? It said class dictionary, right? And the name of the file is point in location constant polymesh. So what we will have now is 15,680 entries, starting with an open round bracket for a normal list, and then it goes open round bracket X, Y, and Z location in the mesh. Okay? Now, in C, all the numbering starts from 0, so I will refer to that as point 0, 1, 2, 3, 4, 5, etc. All the way to the bottom. Where I'm going to have close round bracket. Okay? Got it? So this is a list of 15,780 XYZ location. Okay? In the second file, I'm going to have faces. See it here, foam file, class face list, object faces, and my faces are what? First 30,000 faces, open round bracket, 4 indices. Okay? These things here are indices of points in the point list. And if my face 0 has got 4 points, that means it's a quad, right? What does a hexagon look like? It says 6, blah, 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 6 labels. Anything easier than that? No. Okay? The third thing that I have is my owner and neighbor list, which will tell me the cell to the left and the right of my face 0. Okay? Okay? So you see here it says that the face to the left of cell to the left of face 0 is 0. But even more interesting, in the comment I will now have a note saying in my mesh there is 15,680 points, 15,200 internal faces, 3880 all faces, and in the end 7,680 cells. Okay? At that point, make sure that you have converted the correct mesh out of Fluent. Okay? Which we have. And now we're done with my mesh, apart from one thing. Okay? Boundary file. Object boundary, class, polyboundary mesh. Can you tell me what is going to be in here? Three patches, open bracket, the first patch is called WoW, open curly bracket, close curly bracket, type WoW, 160 faces in the patch. What will that be? Well, that's my airfoil, right? The second thing, pressure far field, type patch, 160 faces, the same as here. Now, what does that mean? It is an O mesh. You know what an O mesh looks like? No? I'll show you in a minute. Okay? And I have a third patch called front and back planes, which is of type empty. Now, what does that mean? Basically, what it's telling you is that in foam, all the meshes are 3D. Okay? And if I have a 3D mesh, for 2D, I'm going to have one layer of cells. What is the boundary condition at the front and the back? There should be symmetry plane, right? But that's insane, because then I'm going to store all the values for the inside, and again all the values in the back, and then all the values in the front. So to avoid that, we have a special boundary condition called empty, which means do nothing, right? And if my mesh is properly 2D, then I can operate only with the faces in the XY direction, and forget the faces in the Z direction. However, if my mesh is 3D, I cannot use an empty boundary condition. Okay? Before we go any further, shall we take a look at that mesh? For that, I'm going to go back to the case directory. What is the case directory? It is the one where you can see the constant and the system. And I will use my post-processing tool called OpenFOAM. I use the native reader option just because I like it. Have you seen one of these before? So here on the left-hand side, I have controls. And down here, I have the parameters that I can use to visualize the mesh. Okay? Take a look at here, mesh regions. Internal mesh, wall, pressure far field, front and back planes. Does this look familiar? Yeah, well, those are my entries in the boundary file. Okay? So I'm going to click here to select all of them. and I will click on apply, and here is my mesh. I will color it in white. It's a bit boring, so I will change the visualization to surface with edges. And now you can see what an O mesh looks like. Where is the business? Click here on this zoom tool. Zoom into the airfoil. Zoom again. Okay, I will center this tool. And watch now, I'm going to turn the thing a little bit. And now you can see that my mesh is actually three-dimensional. See it? Okay. I'm going to change the visualization to outline, zoom out, and then here under filters, alphabetical, I will use a tool called extract block. There we are. And I will extract the patch called wall. You see? I can also extract the far field. And now you can see the visualization of my mesh. Okay, just to make sure, are you logged into the system? Can you try and fire up Parafoam? Does it work for you? No? Shall we fix that after the break?
Yeah, cool.
Okay, good. Right. So now that we have the mesh, let us take a look at the fields in the 0 directory. Okay, so the first field that I want to take a look at is called U. Does it look familiar? I will ignore this one for the last time. Class, volume vector field, object U. Dimensions, meters per second. Internal field, 1, 0.10. And then boundary field. Which has got those 3 entries that we spoke about. Okay, remember, wall, this is my profile. The type of the boundary condition on the wall is fixed value, and the value is 0. I have a pressure far field boundary condition where I use the inlet-outlet boundary condition. More on that later. And I have front and back planes, which has got type empty. Now, what will be a boundary condition on P on front and back planes? Well, the same, right? Because if it's 2-dimensional for the velocity, it must be 2-dimensional for the pressure, and for K, and for nu T, and for all the other fields, which is why empty was specified in constant polymesh boundary. Okay. What about the boundary condition on the velocity for the wall? Well, now we have to start talking about the physics that we are solving. In this case, we are solving fluid flow. And if I fix the velocity, I cannot fix the pressure. So if I look at the boundary condition for the pressure on this patch, it will live where? 0/P. And here I have class volume scalar field, object P, dimensions 0, 2, minus 2. Is this Pascal? No. Okay, because in incompressible flows, I have divided my equations by the density. Okay, so this is Pascal over kilograms per meter cubed, which will give me this 0, 2, minus 2. Internal field, uniform, wall, boundary condition, 0 gradient. Okay, velocity set fixed value. And front and back planes, it says empty. Okay, why didn't I just say wall? Well, we said that we are going to use the tools which don't know which equations you're solving. Okay? And an inlet or a wall boundary condition for the flow means something completely different than it does for structural analysis. First, depending on the fields that I'm solving. And second, if I switch on the buoyancy, for example, then the boundary condition here will not be zero gradient anymore, because that's not consistent in the solver. Okay? So each of the solver carries the physics, which carries the boundary conditions that you need to have, and it is necessary to think about it. What about the turbulence? Okay, so for turbulence, I have two fields. The first one is K, where I'm going to have dimensions meter square per second square. Why? Because this is the square of the velocity fluctuation. The velocity is meters per second. The square is meter square per second square. And the value will be 0.0038. What happens if I put 0? Well, this is an invalid value for turbulence kinetic energy, and the code will fail. Okay. What about the boundary conditions? Well, pressure far field, I will use this famous inlet-outlet boundary condition. And on the wall, I want to use the wall function. Okay? Let's take a look at some discretization controls quickly, and then we will run the solver. Okay. So when I get out of the 0 directory, in the system directory, I have FV schemes. Take a look at it here. It says class dictionary. Okay? And it says DDT schemes, grad schemes, div schemes, and there is a whole bunch of them. Okay? Now, because this is a dictionary format, the order of entries does not matter. Okay, so you can take grad schemes and put it down here. Everybody's happy. You can put phi k first, phi u last, etc. The code will take care of it. But the right-hand side must be the specification of a valid scheme. Okay, so for those more experienced people running FOAM, what is the first application that I will run? Anyone? Check mesh. Exactly. Thank you. So what does check mesh do? It will check the mesh, and the way I usually run this is as follows. Okay? Check mesh, vertical line or a pipe into a T-junction, where one part of the T-junction puts things into log check and the other part puts it onto the screen. Why? Because if something goes wrong, I like killing my application with Control-C, but I still want to be able to see what was printed on the screen, so that will give me a copy in log check. Okay, by the way, there's one thing that I forgot to ask you. Do you know Unix? mkdir, cd, ls, vi, find, dot, minus, type, grep, blah, blah, blah. Very impressive, thank you. Okay, so when I run check mesh, I will get a bunch of output that looks like this. Familiar? Familiar? We don't have to keep talking about that. After that, it will say, create time. What does that do? It reads system control dictionary. Okay, sets time to whatever time was there. Okay, time is 0. It reads the mesh and it says you have 1568 points, 3880 faces, 7680 cells. Okay? That's the mesh that we read in. Everybody is happy. And then it will tell me a bunch of parameters. You have 7680 tetrahedra, 0 other cell types. It will check that the mesh is correct, and it will check how many patches I have. It will report patch, faces, points, patch area, surface topology, so that now I know that my patch wall has got a total area of 2.5 square meters, for example. Page down. Checking geometry. This is a 2D mesh. How does it know? Well, I have an empty patch. Okay? The empty patch will tell me that I will solve for the X and Y direction, but in the Z direction there is nothing for me to solve. Okay? It will also tell me that the boundary openness is 0. What does that mean? If I go into the mesh and sum up the face area vectors of the whole of the outside boundary, I should get, well, 0, right? It's a closed body. Okay? I will also do the same check for all the cell, and I will report maximum cell openness. Where are we? High aspect ratio, boundary openness, blah, blah, blah. Minimum face area, max volume, total volume, cell volumes, okay. And it will also report, it looks like it didn't report cell openness because all the cells are closed as well. Aha, here we are. Number of cells. Number of severely non-orthogonal faces, 77.9. There are 60 such faces in the mesh. Now, keep in mind, this tool was written in about 1995, when a 10,000 cell mesh was reasonable and 77 degrees non-orthogonality was large. Okay? So the tool is very paranoid, and it will complain about lots and lots of meshes which are perfectly fine. Okay? The parameter that is important in the whole story is this one here, which is the maximum non-orthogonality. Okay? Would you know to tell me what that means? Anyone? No? Okay, so we will talk about non-orthogonality in one of the future lectures. But the important thing is that it needs to be less than 90. Okay, because if the non-orthogonality is greater than 90, your mesh is formally invalid. Okay? In industrial strength meshes, reasonable numbers for non-orthogonality are 80, 85 degrees. I rarely see the meshes where it's below 70 degrees, and foam will run just fine. Okay? I will do the discretization best practice presentation to show you what this exactly means, but don't be scared. Okay? The second one, which this one complains about, is high aspect ratio cell. You know what that is? It's a long, thin cell and it compares delta X to delta Y. Okay? Now, do you want cells like that? Yes, you do, right? Because I'm going to have an airfoil, which is 1 meter long. Okay? And the boundary layer thickness on that airfoil is going to be 1 millimeter. Okay? So in order to resolve it, I want long, thin cells. This one will complain when the cell aspect ratio is greater than 1,000. But 3,500 is actually moderately high. Okay? This one does not degrade your accuracy, but you have to be careful because the precision of XYZ point locations in constant polymesh boundary will become important. Okay? When do you start worrying about this number? Well, when it's 100,000 and you write in single precision, then you lost 5 out of 6 decimal places, so write double precision. But more than 90% of all the users run double precision anyway. What's the highest number that I saw? 2.5 million. Why is that? Because we had a ship length 360 meters, boundary layer length 20 centimeters, you have to capture a low Reynolds number next to the wall, and the code still ran fine. Okay? So this is mainly to check whether your mesh is completely insane or not. But the really important number here is the max non-orthogonality. Another number that I look at all the time is this overall domain bounding box. From minus xyz to plus xyz, minus 24 to 25 meters. Okay, this is in meters. Sometimes people in outside mesh generation will build the mesh in millimeters, in which case you need to scale it down. Okay, so later on I will show you a piece of engineering equipment which is 1 kilometer long. Is that possible? Well, if it's a bridge, maybe yes, but a piece of engine which is 1 kilometer long, no. Okay, so please take a look at that number and say, is this sensible? Is this the mesh that I wanted to look at? Okay, so now that we have checked the mesh, the executable that I wish to run is called potential foam. Okay, with potential foam, I can initialize my flow field. Okay, but I'm not sure whether I'm going to bother or not. Okay, so the solution that I really want is the solution of incompressible, steady turbulence flow, and for that the solver is called simple foam. Again, pipe T log. Okay, enter. Look at the beginning of the story. Header, build, exec, blah blah blah, and various other parameters. And then it will say things like create time, create mesh for time 0, reading field P, reading field U. Can you figure out what's going on? So create time, reads system control dictionary, says start from, start time 0. Okay, and then it says create mesh for time 0. Why is that? Well, you can have transient simulation of flapping wings where my mesh changes, right? So in that case, not all of the mesh will live in constant polymesh directory, but it will live under time directories as well. And I need to know which piece of the mesh that I'm going to read. Then it says reading field P, reading field U, reading calculating phase flux field phi, more on that, selecting incompressible transport model Newtonian. What's that? Well, I need to know material properties, in this case viscosity. Where does the viscosity live? In the constant directory. Okay? So jump back into my case, take a look at the constant directory, and interestingly here I have transport properties. Foam file, class dictionary, object transport properties. But there is something interesting going on here. The first thing it says, transport model Newtonian, and Newtonian viscosity nu is a dimension scalar with the value 10 to the minus 5. Dynamic viscosity or kinematic viscosity? Why? Because dynamic viscosity has got dimensions of Pascal second, and this one has got dimensions of meter square per second, so it got divided through by the density. You know that this is a kinematic viscosity. Also note that it's got a name. Right, now, what are these additional things here? They're called dictionaries, right? And the next one is called cross power law, which is another type of transport model or viscosity, which happens to be non-linear. Okay? But now that would mean that if I switch from Newtonian to cross power law, one entry is not enough, I need to have many entries. So rather than reading from the same dictionary, the cross power law entry here will drop me into cross power law coefficients dictionary, and I can read in nu 0, nu infinity, m, and n, which are the parameters of the cross power law model. Do I need this at the moment? No. Okay, because the Newtonian doesn't read that part of the story. Okay, but I kept it here to show you that, for example, the Bird-Carreau viscosity model and cross power law both have something called nu 0 and nu infinity, but they have a different meaning. That one has got m and n, that one has got k and n. Okay? So in a whole set of parameters, you're going to have the main transport model, which refers to transport model coefficients, and then the coefficients entry where the code gets ready. Okay. The second thing that I had was the choice of a turbulence model, and it says selecting RAS turbulence model K epsilon with K epsilon coefficients blah blah blah. Where does that live? More constant RAS properties. Okay, and here you have the same story. The RAS model is K epsilon, turbulence is on, Prit coefficients is on, and the K epsilon coefficients are down here. What happens if I just want the default coefficients? Well, I delete that part and the code will happily carry on running. Okay, so let's take a look at the code actually running. Okay. So it will say something like time equals 14, BCG stub solving for ux. Can you tell me what that is? X component of the velocity. Initial residual 0.048, final residual 10 to the minus 11, number of iterations 3. BCG stub solving for uy, initial residual blah blah blah, final residual blah blah blah, number of iteration 3. ICCG solving for p, initial residual this, final residual that, number of iterations 1, 3, 1. Then solving for epsilon, solving for k, execution time, clock time, etc. Okay, notice that my execution time is 0.75 and clock time is 313 seconds. Why? Because I've been talking for 5 minutes, right? As I keep running this, in my case directory, I will see time directories appear. You see? 50, 100, 150, 200, let me stop that, okay. And in the time directory 200, what do I have? My results, okay. Notice, U, K, P, epsilon, nu T, phi, all the fields that I have created during the simulation. Okay, obviously, in the 0 directory, I said the velocity is 10.10, and it is uniform, but here it is not. Okay, so let's take a look at what that field looks like, or if you like, let's take a look at your velocities. Okay. Class, volume vector field, location 200, object U, dimensions meters per second, internal field, non-uniform list of vectors, and X, Y, and Z components of all of those vectors in the field. Happy? Well, not really. I want to see what my vectors look like and not just look at the X, Y, Z values because I'm good, but I'm not a robot. Okay, so what we're going to do now is fire up ParaView again. Back to the case directory, para foam minus native reader. Okay, read all the components. See down here I have the fields. Click on it and look, my pressure is constant. Why is that? I am in time step 0. Okay, so I'm going to click on this button here. And now rescale. And when I zoom in, you can see my pressure field. Click here, U. Here's my velocity field. New T. Here is my turbulence kinetic energy field. Turbulence viscosity field. Okay. If I go and click play, you can see how the flow is developing. Got it? Go back to my run. Resume the run. And it will say reached convergence criterion 0.01 in 379 iterations. And now, apart from 0, 50, 100, 150, 250, I also have 379 because I have reached convergence. Happy? Right, well, I want one more thing that's not happening here. I want to see those little graphs of the residuals going down, right? So first let's do it manually. Okay, so to do that, I have a tool called foam log. And I'll give it the name of the log file, and then in the logs directory, it will give me a list of analysis of my log file, and I can do something like this. Okay, rescale my y-axis to be logarithmic, and I can follow the residual graphs going down. Okay, well that's okay if I need to do a paper and I need residual logs. But really I want my residuals to be updated on the screen in front of me, right? And because the solver doesn't know about it, we use a set of tools called PyFoam to do that for us. But in order to show you that, I have to have something that runs a little bit longer. Okay? Congratulations. You have done your first run.